Hey guys, welcome back to videos. We are in Module 1, Lesson 16, Relating Scale Drawings to Ratios and Rates. I just put up scale drawings. There is a very good possibility, as I pull out my handy dandy binder, that we will be testing sometime next week. So it is Wednesday. We've got to get through, as I take a look here through my handy dandy binder, Lesson 16, Lesson 17, Lesson 18, Lesson 19, Lesson 20, and we may or may not do 21. So we've got 5 lessons, approximately. Next Friday is probably a good day for a test. So hear that again, next Friday is probably a good day for a test. So before we even get started on the packet, here's some things that maybe you don't remember or maybe you should remember. Can we see everything? Heck yeah, we can. So first off, a scale drawing. Okay, the way that I like to think about scale drawings are blueprints. So I worked a lot for my father's painting business where I had to read whole buildings based off of blueprints. They can't obviously give me a piece of paper that shows the actual whole building, so they've scaled it down. They've made it smaller. Scale drawings can be a couple different things. They can be blueprints, they can be maps, they can be anything that will have a scale that will help us see them. So anything that has been scaled to size to help us see things. Does this mean that it just can be small, like going from big to small? Absolutely not. Think about some things in science that are those, like, now I'm not a science teacher, but like bacteria. We can't see bacteria, so they have to make it bigger and bigger and bigger and bigger so that we can actually have an idea of what we're seeing. So there are 2 things that we're seeing. One is what's called a reduction. A reduction is something that has become smaller. So the blueprints that I was looking at took a building which was truly, like, I think it was a 12-story building for the Pitt Towers at the University of Pittsburgh. It's where freshmen used to stay in their dorms, but it had rooms that we were painting. But it was the Pitt Towers, so it was 12 floors up. And they reduced these 12 floors down to a piece of paper that I could see. That was a reduction. The other way that we could have it, more thinking about science now, is what's called an enlargement. And an enlargement is exactly what it's doing. It's making it larger. So this makes something larger. Okay? So we have the scale drawing, which is helping scaling something to a size in order for us to see it better. Reduction makes it smaller, enlargement makes it larger. Now, every enlargement or reduction has what is called corresponding parts. So corresponding parts that must be in the exact same place. So what do I mean by that? Well, here's our example. Let's say we've got this right triangle. So it's right triangle A, B, C, and it's a reduction. And then we've got X, Y, Z. Well, notice that point A corresponds to point what? Well, okay, so are they the same direction? Yeah, they're the same direction. Okay, so A up to point X. Okay, that's what corresponding means, in the same place based off of what we're looking. Sometimes You might get something that looks like this though. So you might get this guy, and then you might get this guy. And you're going to say, okay, well, how do I turn it to make it the right way? So you might have to manipulate these figures. Manipulate means moving them a little bit in order to find what corresponds to what. So these are our basic definitions for this lesson. Scale drawing, something that has been scaled down or changed in size in order for us to see better. Either getting smaller, which is a reduction, or getting bigger, which is an enlargement. Corresponding parts, parts that must be in the exact same place and correspond to each other. Okay? Nice and basic. Constants in scale drawings. Okay? There are constants in scale drawings. Eventually, we are going to call these scale factors. But right now, I think your notes just call it a constant of proportionality still. Let's make sure. Yep, constant of proportionality. So constants in scale drawing are always going to be the original is the x value. The enlargement or reduction is the y. And you're like, what does this look like? Well, this should really resemble y divided by x equals k, where k is the constant. This is what we did at the whole beginning of this module. We're not losing that. But you just need to remember, well, what is going to be my x? My x is the original. No matter how big, so if I'm going back to these, let's say we've got 3, 4, 5, 6, 8, 10. And it might say, is this being the original? First off, you would say, okay, is it an enlargement or a reduction? Well, it's a reduction. How do I know? Because it's getting smaller. Original is bigger than the smaller, even though the numbers don't work, so let's switch that. Don't write that yet. Let's make this make a little bit more sense. 6, 8, 10, 3, 4, 5. See what happens when I try to do this on my lunch break? Like my food's sitting back on the desk. Like you can actually see it. Wait, it looks delicious. Hold on. So my wife's out of town, so I'm making food. It's rice and meatballs with some barbecue sauce. It looks pretty good. So I'm winning at adulting. Like before I met my wife, I couldn't cook to save my life. Okay, so this is what I get for eating half of my lunch and then trying to do this. Stay there. Stop. Stay. I said stay. Stop. Okay, so if I look at this, to find if it's proportional, I need to find the corresponding parts. AB matches up with XY. Well, when I do this though, the XY portion, which is 3, is the reduction divided by 6. That has to stay the same as the next. Well, 10 and 5 match up. The reduction over the original, the reduction over the original. Well, let's see, 3 divided by 6 is 1/2. 5 divided by 10 is 1/2. 4 divided by 8 is 1/2. So my constant is 1/2. Eventually you're going to say the scale factor is 1/2. But right now, all you need to understand is we're still doing this same thing to find the constant, except now we are using this model here. I don't know what your homework is yet. We'll determine that once you're done watching the video. Happy Wednesday. Woo-woo! Yay.